We're going to cover the SIR method. SIR stands for susceptible, infected, recovered. This is the model that epidemiologists use to model the spread of COVID or swine flu or any other viral infection. We've covered the exponential model. That's inadequate because it just continues to grow without bound, and eventually our population's limited. And just to catch you up, we talked about the logistic growth model, but the problem with logistic is once infected, always infected. And that could be true with a bacterial disease, or possibly a zombie apocalypse would be model with logistic growth. You can call that the SI model. This was called a compartment model. People fit into compartments. This is also called a compartment model. We're just adding one more compartment. They're recovered. Okay, people eventually recover, and then they're taken out of the pool. They recover. They're neither infected nor susceptible. That happens with most viral infections. I've been told the only problem is sometimes a virus can mutate far enough away from the original strain that a person can get reinfected with a much different mutation, but you can consider that a different disease, I guess. So we're assuming that once a person recovers, they're not going to get the original disease. So here's some variables. S of t is a number susceptible at time t. I of t is a number infected at time t. R of t is a number recovered at time t. And this should equal the total population. Every person is in one of these categories. And generally, they kind of migrate from here to here to here. Tau is a contagious period, 5-7 days. I would guess it depends on the disease. It's going to be the average contagious person. It can vary from person to person, but we have to make some assumptions. We'll just assume an average. RE is going to be the initial effective reproduction number, and I said initial. This is really a function of time. I could put of t here, and but I decided to leave that variable out. We're just going to assume that. One interesting fact. RE is actually used in the UK. R sub t is used in the United States. It's the same variable. When I researched all this, I couldn't find any references in the US. The only thing I could find was in the UK, so that's why I used that. But if you read some literature in this country, you'll see it's R sub t. It's the same thing. And t is probably a better choice because it varies with time. As time goes on, as more and more people become infected and recovered, that slows down the spread of the virus. There are less hosts available. So now initially in this problem we have 500 people with 100 vaccinated, and we're going to assume it's 100% effective. And 5 are initially infected. We're going to assume tau is 5 days. So we're going to fill in all these parameters. First of all, if 400 are vaccinated, we're going to take or 100 are vaccinated, we're going to take 100 out of this pool. You can basically just knock that down to 400. We have 400 people that we're going to do this viral experiment on. The other 100 that are vaccinated, they're off to the side somewhere. We don't even need to consider that they exist. So for the whole experiment. Now, it turns out the number infected are 5 are initially infected, so, and we'll assume there's 0 recovered. We're not going to worry about that. And let's assume, I didn't give you the initial reproduction number. Let's assume the reproduction number is, the effective reproduction number is 2.0. And that takes into account how fast the virus spreads, what population we have. But this is taken into account the 100 that are vaccinated that are removed. If that effective reproduction number were based on 500 people without vaccinations, then doing the vaccination would change this number. So, but that's taking into account this. Now, if we have 5 infected, 0 recovered, we have 400 people in our viable population. This is going to be 395. Is a number susceptible. That's how many can catch the disease. 5 is how many people have it. And we have 0 recovered. Well, the first thing we want to do is calculate these coefficients. We use these coefficients in our model. It's nice to have a decimal here and a decimal here. It just expedites things. And so this is going to be 2.0 divided by tau is equal to 5 times. Now, this is the initial state of affairs, 395 and 5 and 0. This is always the total population. So that's 400. Now we need to divide 2 divided by 5. And we end up with 0.001. And then 1 over tau is 1 over 5, which is 0.2. It's nice to have that. Now day 0, this is like right at the beginning. We have the number susceptible are 395, the number infected are 5, number recovered are 0. And this is basically new infections. I skipped a heading here. This is how many are infected. This you should recognize, susceptible times infected. That was what we calculated. That's a number of possible interactions between those that can get it and those that have it. We already went through that with logistic growth. And this replaces our proportionality constant, C that we called it. It's just that now we've connected that C with these epidemiological variables, R sub E, tau, and how many people we start with. Okay, it's nice to be able to just plug these right into the model. And so we're going to have this coefficient 0.001 times 395 times 5 equals, now we have to calculate that. And I have 1.975. I'll just round that up to 2. We'll round this to the nearest person. So we have 2 new infections. And now we have to do 1 over tau. These are actually the recoveries. The whole idea here is we have 5 people, and they're infectious for 5 days. Guess what? Whatever the infectious population is, every day 1/5 of them becomes recovered. Takes a person 5 days. We're just going to take 1/5 out of this pool. So we take 0.2 times the infected population. Okay, and that's equal to 1. And again, we'll round that off to the nearest whole number. So now we have to do some recalculations. How many are susceptible? Well, we started with 395, but we have 2 new infections. So guess what? 2 people move from here to here. So we do 395 minus 2 is 393. I'll move these numbers down a little bit. How many infected? Well, guess what? We have 2 new infections, but this person left the building. And so this is going to be 5 plus 2 minus 1, which is equal to 6. Okay, and then the recoveries, well, we have to take 0. This is the recoveries rate here. So we have to take 0 plus 1 equals 1. Okay, and those are our new numbers. Let me box these in. Now, how do we calculate the number of new infections? Well, we're going to do 0.001 times 393 times 6. Okay, 393 times 6 times 0.001. It looks like I get 2.35, so we'll round that off to 2. You could keep track of decimals here if you wanted a more accurate representation, but we'll just use a whole number. And then we have, let's see, we have 6, 0.2 times 6, and we'll round that to 1. That's 1.2, but we'll round it to 1. And then we go on to the second day. I'm not going to continue this all the way down, but we have 393. Okay. We have to subtract out the infections. 2 of these bit the dust. Okay, so that's 391. And then we take our number infected, and we have to add 2, subtract 1. It's this 2 and this 1. In the text, I draw arrows so you can see this. 6 and 2 is 8, minus 1 is 7. Okay, and the number recovered, well, guess what? We had this person still recovered. Okay, nothing happened to them. And we have a new recovery, so we have 1 plus 1 equals 2. And there's our new state of affairs of the virus. And then you can continue. Obviously, this isn't something you'd want to spend a lot of time doing by hand. Very easy to automate all this with a spreadsheet. Marker cap here. Very, very simple, very repetitive. You can build a spreadsheet, change all these parameters here. In fact, in chapter 12, I did some spreadsheet projections to show you. One way in which COVID is different from the flu is this reproduction number here. The basic reproduction number, I think, is probably around 4. The effective reproduction number, that's a good question. The problem is, currently with COVID, we don't know how many people are immune. There's a lot of sources of immunity for a virus. One could be genetic, one could be prior exposure to other viruses. Initially, they thought that was pretty low. But if you follow this model forward like 3 to 4 months into the future, you can see the difference between a basic ordinary flu, where this is 1.5, you're talking, tens of thousands, maybe 100,000 infections. Whereas if this ramps up to 2 and 3 and 4, you can have 10 million infections or 100 million infections. It really speeds things up. And that's really what concerned the epidemiologists with COVID, was that they were looking 3 months into the future, and if we took absolutely no precautions, our medical system could shut down, hospitals could be overrun, and then doctors walk off the job, and we could be in the position where we had no hospitals, especially in urban areas. So this was used. There was actually 2 models, early models in the UK. There was the Oxford model and the Imperial College model. Both of them made assumptions. Early on in the disease, you have to make some assumptions. The Imperial College model assumed a late introduction of the disease and also no prior immunity, and that was much more serious. That's what public health officials went by, and that was a worst case scenario. The Oxford model, both of them used the SAR, they just had different assumptions about when the disease started and how many people had some sort of immunity. So, but both of them used the SIR for their projections. So if you're interested, you spend a little bit of time working with this, you can understand what's going on in public health from the epidemiologist standpoint. Okay, you just have one problem grinding through 5 days. They put the answers for the 5th day down here so you can check your work. And that's all we're doing with with this. It's some terrific modeling to see this whole process, whole cyclical process of models, starting with exponential, going to logistic, and then ending with SIR. So